Good afternoon. Today we will continue with the next topic in the unit, which is sets. So for sets, the topic is something that we have already studied in earlier classes, and you already know the topic. So we'll just revise the basic concepts of sets. Now, what do you mean by sets? Sets are always used to group objects together, and usually all the objects that are grouped together in a set, they have similar properties. So the set in mathematics, the objects or the numbers which are grouped together, they have similar properties. And sets are the fundamental discrete structures. So why do we need to study sets in discrete mathematics? The reason for studying sets in discrete mathematics, because these are the discrete structures on which all the other discrete structures are built. Example, relations, graph theory, etc. So these are the basic discrete structures on which other discrete structures are built. And let's look at the basic example of sets. The example can be all the students of your class. It can be denoted by the set A, all students in section A. Similarly, set B can be all students in section B. Another example can be the Department of Computer Science Engineering, or D, the students in ISL Engineering College. So these are the different examples of sets. Okay, now let's just move on with the examples of the slide. So all the students who are currently enrolled in your school make up a set. All the students currently taking a course in discrete mathematics make up a set. Okay, now let's see the formal definition along with the notation. So if we want to define set, we usually say that it is an unordered collection of objects. This is very important, that a set is an unordered collection of objects, and those objects are also called as elements or members of the set. And a set is said to contain elements. Okay, now if you have a set A with 3 elements A, B, C, then whenever you want to denote whether an element is there in the set or not, you say A belongs to A. Suppose X is not in the element in the set A, so X does not belong to A. Okay, so these are the two notations: A belongs and does not belongs. Next, let's see an example. So the set of vowels. The set of vowels will be, we have 5 vowels, so A, E, I, O, U. What about the set of even numbers from 1 to 10? So even numbers from 1 to 10, let's denote it by the letter E. So always when we are denoting a set, we use the capital letter. And here are the even numbers from 1 to 10. So it will be, since we are taking 1, so 2, 4, 6, 8, and 10. Okay, so these are the even numbers from 1 to 10. Similarly, let's see the examples. So it's a set of all vowels is being denoted by V, A, E, I, O, U, and the set of odd positive integers less than 10. So over here, since we have less than 10, we have 1, 3, 5, 7, 9. Okay. Now the next thing is, what about some other notation? So we have, this is the generally defined notation. There is another notation which is known as set builder notation. So another way to describe a set is by characterizing all elements by some property or the properties. Okay, so generally whenever we have a set, we describe or characterize it by some property. as I have said earlier, that they usually have some similar properties. So over here we are characterizing it by some similar properties. So suppose if you are saying set E is all even numbers, even positive integers less than 10. In that case, you can write it as x such that x is an even positive integer less than 10. Or we can even describe it in this way, or E is equal to x belongs to z plus such that x is even and x is less than 10. Okay, so these two notations are known as set builder notations. Okay, these two notations are known as set builder notations. Another example is set. Over here, instead of even, we have odd positive integers, so the same kind of notation. And these are the notations when we have a set which is larger than its normal size. Then if we say set O of all positive integers of less than 100, so we can't go on writing all the numbers, odd numbers less than 100. So in that case, we just use the set builder notation. Okay, now we will see a few places where we usually use set builder notations are in these cases. Next, we will see some kind of important sets which are used in discrete mathematics. So each denoted by a capital letter, and which are important in discrete mathematics. Set of natural numbers which begins from 1, positive 1 till infinity. Sometimes even 0 is considered, so it is a person's intention whether he wants to include 0 or not. Now the next thing is set of integers, so it includes both the negative numbers and positive numbers. Then we just have positive integers denoted by z plus, rational numbers which is in fractional form, then the set of real numbers, positive real numbers, and complex numbers. Okay, this is not to be remembered, it is just for the use of information that these are the sets that are usually used in our subject. Now, what about the intervals? This is also something that you have already studied. We'll just revise it. So suppose if you have two numbers a and b, and a is less than b, then you have something known as closed interval, open interval. Okay, so closed interval means we include the number a and b. Okay, so let's take the example of 2 to 5. A is 2, b is 5. Then if we are writing square bracket 2 comma 5, then it means all the numbers including 2 and 5, 2, 3, 4, 5. Okay, the next one is rounded brackets 2 comma 5. In this case, we don't include 2 and 5, we just include the numbers in between 2 and 5, so it will be 3, 4. And similar way, if we start with a square bracket and end with a rounded bracket, it means we have to include 2 but not 5, so 2, 3, 4. And the vice versa case, where we are starting with a rounded bracket and ending with a square bracket. So in this case, it will be 3, 4, 5. Okay, and the two terms to be remembered are closed interval and open interval. Next, the next topic we'll study different types of sets. So the first will be equal sets. Two sets are said to be equal if and only if they have the same elements. If the elements of the sets are same, that is, if set A has A, B, C, set B also should have the same elements which are A, B, C. Okay, one more thing, since sets are unordered, so B may have BCA, or it can be CAB, anything. But if the elements are exactly the same, then the sets are equal, that is A is equal to B. Okay, next, therefore, if A and B are sets, to express it in the form of predicates and quantifiers, we can say it as if A and B are equal if and only if for every x if X is an element of A or B, if X belongs to A, by implication, X should also belong to B. If this condition is satisfied, then we say that uh, the sets are equal. So we write A is equal to B if A and B are equal sets. Now, why particularly this condition for all X belongs to A? Why are we particularly using the symbol of implication? The reason we are using by implication is, if you remember, the property of by implication is if P and Q have the same truth values, if both of them are true or both of them are false, then it will result in true. Okay, and if they have opposite truth values, then it will result in false. Basically, I'm simplifying the truth table. Now, if you look over here, if X belongs to A is true, X belongs to B is true, that means X is in both A and B. Similarly, if X belongs to A is false and X belongs to B is false, that means X is not in both A and B. That is the reason we are using the connective of implication. Okay, because if X is in A, it should be in B. If X is not in A, then it should not be in B. Okay, so if you want to check for equal sets, you always have to check with the connective by implication. All right, now let's see an example for equal sets. So the sets 135 and 351 are equal because they have the same elements. And if you remember just now, I have said that sets are unordered. Okay, so even if the order is changed and the elements are same, then it will be known as equal sets. Okay, so here is the point: the order in which the elements of a set are listed, it does not matter. Also, if an element of a set is listed more than once, so you have 3 being listed thrice and 5 being listed 4 times, even then both of them are equal because the elements 1 is present in this set, 3 is also present in this set, and even 5. There is no other element which is not in A and which is in B. That is the reason even if the elements are repeated, even then they are equal sets if they have the same type of elements. Next topic will be empty and singleton set. So as the name itself specifies that empty set, it won't have any element. So a special set that has no elements, it is called an empty set, and it is also called null set, and it is denoted by this symbol which is read as phi. The empty set can also be denoted by this symbol, that is a pair of empty brackets, a pair of empty parentheses. Okay, and what is the set empty set example? If you are taking positive integers, okay, which for which x is greater than x square, is there any number which is greater than its square? No. If you are considering positive integers, suppose the example is x is 4. Is 4 greater than 16? No. In this case, all the set of positive integers where the actual number is greater than its square is a empty set because there are no such numbers. Now, what about singleton set? A set with only one element is called a singleton set. So if you have only one element like A or 1, these are known as singleton set. Okay, a set with only one element. Let's see examples for this. The set of all positive integers that are greater than their squares, it is a null set. What about a set with one element? Okay, so this point is important because empty set, if it is inside a set, so if A is equal to set of phi, then this is also known as singleton set. Okay, individually simply phi can be called as empty set, but if it is included in some set, then it will be known as a singleton set. So this is an important point and a confusing one, but if you understand it, empty set by itself is a empty set, and if you include it in with a pair of brackets, then it will be a singleton set. Now, Venn diagrams. So whenever we are speaking about sets, To represent them graphically, we have something known as Venn diagrams. In Venn diagrams, the universal set is U. Okay. In Venn diagrams, we have something known as universal set, which contains all the objects under the consideration, and it is represented by a rectangle. So universal set is U, represented by rectangle. Inside the universal set, we represent our sets. Sets are represented by circles or any geometrical figures. Okay. Inside the rectangle, we use circles or any other geometrical figures. Sometimes we also use points to represent the particular elements. And what are Venn diagrams? Venn diagrams are used to indicate relationships. We will study relationships of sets in the next topic. So for now, you just have to remember that Venn diagrams are usually used to indicate relationships. Okay. Now the next thing. Whenever you want to represent Venn diagrams, we will see one of them now. So if we want to describe Venn diagrams for set of all vowels. So V is equal to A, E, I, O, U. And I want to represent the set of all vowels using the Venn diagram. Let's see that. So to describe the set of all vowels, first we have to draw a rectangle. Okay. First we have to draw a rectangle. Okay, now this rectangle is our universal set U. Now inside this rectangle, we have to draw a circle. Okay, circle to represent our vowel set. After that, let's name the rectangle and the circle. This is our universal set U, and this is our set of vowels V. Now what is the universal set in this case? Universal set in this case is the set of all alphabets. So in set builder notation, it can be represented as X, such that X is the set of all alphabets. Okay, so this is what U indicates in our Venn diagram. Now what is V? V is something that we have already defined. It is the set of all vowels. Now in this case, what are the vowels? We can denote them by points A, E, I, O, and U. Okay, so this is the Venn diagram for set of all Venn diagram for set of all vowels. Okay, this is the way you are supposed to represent the Venn diagram. Now let's go back, and the next topic that we are supposed to study is subsets. What is a subset? The set A is a subset of D if and only if every element of A is also an element of B. Normally, whenever we are dealing with sets, it is commonly we see the situations where we have to show that the elements of one set are also the elements of a second set. To express this terminology, we are using the term subset. Okay, subset is basically when element in A is also in B. Okay, and to indicate the subset, we use the notation of a U, inverted U, and along with an dash. So over here, A subset B, it means that the elements of A are in B. Okay. For this, the quantification that we generally use is for all X, if X is in A, so this can be represented as if X is in A, then X is also in B. Okay, this is the way we express the quantification. And whenever we are dealing with sets, the set of, let's see an example. If set A is all odd positive integers, all odd positive integers less than 10, and B is all integers less than 10. Okay, then A is a subset of B. Okay, and the subset of B is denoted by using this kind of Venn diagram. So the Venn diagram for the subset is denoted in this way. Okay, over here, if A is a subset of B, then the inner circle is A and the outer circle is B, and this is our universal set. Okay, that means over this A is all odd positive integers and B is all the positive integers. All right. Now let's see an example. So example is the set of all odd positive integers less than 10. If we are considering this part as our A, then it is a subset of all positive integers less than 10, which is our B. Okay, and this is the diagram, Venn diagram, that I have showed you earlier. Now whenever we are dealing with subsets, any set is guaranteed to have two subsets. Okay, whenever we are dealing with subsets, any set A or S, it is guaranteed to have two subsets. So if the set is S, okay, and it consists of the elements 1, 2, 3, okay, then empty set which is having nothing, okay, which contains which is a null set, it is a subset of S, okay, and also the set itself is also a subset of S. Okay, so for every set there are minimum at least two subsets. Okay, the empty set and also the set itself. Now for every set we have to prove that there are two sets. There are two subsets. How can we prove that? Let S be a set. To show that the null set is a subset of S, we must show for all X belongs to empty set implies X belongs to S. Now from where are we getting this property? This property was from here. Whenever we are supposed to show our quantification of subsets, we take this. For all X, if X belongs to A, then X should also belongs to B. Okay, so now we have to show it with respect to empty set. Because the empty set contains no elements, okay, X can't belong to empty set. There are no elements in the empty set. That is the reason this part is false. Okay, now this part is false. Whether this part is either true or false, it can be either true or false. But we know that if in the case of P implies Q, if we remember the truth table for P implies Q, PQ, look at the last two rows. If P is false, whether Q is true or false, it will be true. Okay, this entire quantification will be true. If the first one is false, P which is also known as the hypothesis. Okay, we have studied it in the first topic that P is the hypothesis. So basically what I am saying is if hypothesis is false and conclusion, so Q is known as conclusion or consequent, and conclusion is true, then whatever conclusion is either true or false, your implication will be true. Okay, so this is always true. In this case, hence, for every set, this part we have proved. Now we have to prove the second part. For the second part, let me just for this question, I'll just take an example. If S is equal to 1, 2, 3, then the same set S will always be a subset. Why? Because if you're taking X is equal to 1 is in both the sets. Similarly for 2 and 3. So S is always, a set itself is always the subset of itself. The next topic, so before that, let's just see the solution. So this is for the first part. For the second part, you can just take an example. Now, the next thing is proper subset. A set is a proper subset if A is not equal to B. If you have two sets where A is a subset of B and A is not equal to B, that is both the sets are not equal, then we call it as a proper subset. Example can be if A is 1, 2, 3 and B is 0, 1, 2, 3, 4. Now in this case, both of these sets are not equal. They are not equal. In this case, they can be known as proper subsets and they'll be denoted in this way. For A to be a proper subset of B, it must be the case that A is a subset of B and there must be an element in B which is not in A. So over here 0 and 4 are the elements which are in B but not in A. Okay. So if you notice the quantification, we write X belongs to A, then X belongs to B, and there is some element which is in B and which is not in A. So over here we have to write it as not. This is a misprint. Next, to prove A is equal to B, we can show that A is a subset of B and B is a subset of A. Whenever the case is that A is a subset of B, that is all the elements of A, all elements of A are in B and all elements of B are in A. In these two cases, if we can show these two subsets, then automatically it means that A is equal to B. Or you can even remember the by implication which I have shown you earlier for equal sets. So the quantification will be with respect to by implication. Next, one more note to be remembered is sets may have other sets as members. Okay, so over here if we have A, if B is A comma B, then A can be a set of empty set, single element A, single element B, and the entire set AB. Okay, so X and B is a subset of A comma B. Over here, note that the two sets are equal because the set of A belongs to A, but simply A does not belong to A. Okay. Now, why are we calling these two sets as equal? Because B is equal to, here the statement means the set B is a subset of A comma B. So if you remember, what are the subset of this set A comma B? It can be the empty set, the entire set, and even the individual elements of the set. Okay, so in this case, B is similar to A, hence we are calling these two sets are equal. Okay. The next thing is cardinality. Now, what do you mean by cardinality? Cardinality is a term that is used for the counting problem. Okay. Sets are usually used in counting problems, and for such applications, we need to discuss the sizes of a set. So whenever we need to discuss the sizes of a set, then we come to the topic of cardinality. So if a set S has 3 elements, then the cardinality of S is denoted by the symbol of modulo and is equal to 3. Let's see the definition. If there are exactly n distinct elements, now the term over here distinct is important. Elements in S where n is a non-negative integer, then we see that it is a finite set and n is the cardinality of S. Now, why are we speaking about finite set? Because for infinite sets, you cannot count the cardinality. So for infinite sets, the term cardinality cannot be used. Okay. And that is the reason we have to take a finite set. And also, if we want to know the cardinality, the elements should be distinct. Okay. Let's see a few examples. Let A be the set of odd positive integers less than 10. So if you know odd positive integers less than 10, then A will be 1, 3, 5, 7, 9. How many elements are there? 5. And since you know the symbol is this, so A is equal to 5. The cardinality of A is 5. The next one, S be the set of letters in the English alphabet. So English alphabet has 26 letters and all are included in the set S. That means the cardinality of S is 26. What about null set? Since null set has no elements, cardinality of a null set will be 0. Okay. The next will be infinite and power set. What do you mean by infinite set? A set where you cannot count the number of objects or elements in the set, it is known to be an infinite set. Like the examples we have seen, the set of natural numbers, n, or the set of real numbers, the set of integers, all of these are infinite set. Okay. And what do you mean by power set? If you have a set S, the power set is the set of all subsets. So if you remember the example of S is equal to A comma B, and we are creating a set of all subsets, let us denote it with A, which is phi, the set of single element A, the set of single element B, and the set of complete elements A comma B, then this A is known as the power set of S and denoted by P of S. Okay. Now let's see the examples. So the set of positive integers is also an infinite set. So Z plus, it is all the positive integers till infinity. And similarly, the example for power set, what is the power set of 0, 1, 2? So the power set of 0, 1, 2, let's solve it over here. So we have to find, suppose the set is A is equal to 0, 1, 2. What is the power set of A? Power set of A. Okay. In the case of power set of A, we have to start first and foremost with the empty set. Okay. Then we have to start with each of them. So 0, then 1, and 2. Okay, now both of them together, so 0 1, 0 2, 1 2, and then at last the entire set 0 1 2. The reason we are including these two sets are because you remember the theorem where the set has at least two subsets. One is the empty set and the other is the set itself. Okay, apart from that, 0 is a subset of A because 0 is in this set and 0 is in the set A, and similarly you can verify for all the elements of the set P of A. Okay, now the next thing is we will see an example. What is the power set of the empty set? Okay, and what is the power set of the single set which contains the empty set? Okay, so power set of the empty set means it is asking us for P of phi, and over here it is asking us for P of the set of phi. Okay, so these were the two things I was explaining while we were dealing with empty and singleton set. Okay, this is an empty set while this is a singleton set. Okay, now what is the power set of this? Let's do it over here. The power set of an empty set will be the singleton set. Okay, and the power set of the singleton set, it will have two subsets. One will be the empty set and the other will be the set itself. Now, why are we writing it in this way? Because empty set, if you remember the theorem, set S has two subsets. First is empty set, second is the set itself. So in the case of the empty set, the set itself is the empty set, so that is the reason we have only phi. In the case of the second one, we will have the empty set. This is the empty set, and this is the set itself, which we are denoting with S. Okay, so I hope there is no confusion with respect to this. Now, how should we know? Suppose if we have P is equal to 1, 2, 3, 4. How should we know the number of, let's denote it with A so that it does not get confusing. How should we know the number of power sets of A? How many subsets should be there in the power set of A? The question is, how many subsets or how many elements are there in the power set of A? Okay, so if A has 4 elements, how many elements should be there in the power set of A? So if you remember the example, for A having 3 elements, let's count the number of elements in P of A. There were 1, 2, total 8 elements. Okay, so if we had A had 3 elements, power set had 8 elements. So if you see some kind of relation between them, that is, if A has n elements, power set will have 2 power n elements. Okay, if n is equal to 3, then 8 can be expressed as 2 cube. If A has 4 elements, then power set will have totally 16 elements, which you can do it as an exercise. Let's see the solution for this. This is the node that I was explaining. If a set has n elements, then its power set has 2 power n elements. And the empty set has exactly one subset, while the singleton set will have 2 subsets. Okay. Now, we have to study something which is known as tuples. What do you mean by tuples? Because sets are unordered, okay, the important property to be remembered always is sets are unordered, and we need a different structure. So what about for ordered elements? So for unordered elements, we have something known as sets. What about for ordered elements or ordered collection? What are we supposed to represent it with? So for this, we are representing it with by the term ordered n-tuples. Okay. Suppose if we have a1, a2, an in the form of an ordered collection, which means a1 is our first element, a2 will be the second, and an will be the nth element. Okay, so these kind of ordered collections are being represented by the name ordered n-tuples. Okay, now what about if we have instead of n numbers, if we have only two pairs, or if we have only two tuples, then they are known as ordered pairs. The ordered pairs can be AB, CD. Example. Now, when are A, B, C, D equal? When A is equal to C and B is equal to C, then the ordered pair will be equal. Okay. And the order of collections is usually important. We will study it in the unit which is known as relations. So for now, we just have to remember that ordered pairs, and ordered pairs are only if we have the tuple of two elements a comma b. The same points have been given over here. So this is ordered n-tuples. Ordered n-tuples are if we have n elements in a tuple, then a1, a2, and so on up to an is an ordered collection. The thing to be remembered is sets are usually unordered, but if we have some kind of ordering, then we are saying n tuples. What does the n indicate? N is the number of elements. And if we have only two elements, then they are known as ordered pairs. And a and a comma b, c comma d are two ordered pairs. And also these two ordered pairs will be equal if A is equal to C and B is equal to D. Similarly, A comma B and B comma A will not be equal until A and B are both the same. The next thing to be the next topic is Cartesian product. What do you mean by Cartesian product? If we have two sets A and B, then the Cartesian product is denoted by A cross B over here, and it is the set of all ordered pairs of A comma B, where A will belong to capital A and B will belong to capital B. Hence, if we want to express it in set builder notation, A cross B is denoted by A comma B such that the first element belongs to capital A and the second element belongs to capital B. Let's understand this with the help of an example. So if we have A is equal to 1 comma 2 and B is equal to A comma B comma C, then what will be the Cartesian product A cross B? Now in this case, we have to consider a small a, which is our element of capital A, and or we can consider x and y because we already have AB over here. So for this, let's consider x and y. So x over here denotes 1 and y over here denotes the elements of B. So let's create the Cartesian product. The Cartesian product will have to be written in this way: 1 comma A, 1 comma B, 1 comma C, and then create the ordered pair with 2, 2 comma A, 2 comma B, and 2 comma C. Okay. Now, another question is, if we have A cross B, can we find out B cross A? Yes. For B cross A, you have to consider the elements of B first and the elements of A later. In this case, we will have A comma 1, A comma 2, and B comma 1, B comma 2, and the same with C. Now over here, a question is whether A cross B and B cross A are equal. No, the Cartesian product of both of them is not equal. That is, they are not equal. Why? Because in the case of ordered pairs, the order is very, very important. And if we have an ordered pair with x comma y, then x should be equal to y. Then only x comma y and y comma x will be equal. Over here, we have x is equal to 1, y is equal to a in the first case, and x is equal to a and y is equal to 1 in the second case. So that is the reason this A cross B and B cross A, that is, it is not equal. Unless and until when will it be equal? When A is equal to phi or B is equal to phi. If both of them are empty sets, then we won't get any Cartesian product. In this case, it will be equal. And also in the case if both the sets are equal, then the Cartesian product will be equal. Okay, so let's see it clearly. So the Cartesian product of E cross B is this, and also the note that both of them are not equal in this case. Unless we have two scenarios, the first one is A is equal to phi or B is equal to phi, and the second scenario is A is equal to B. Now, what is the Cartesian product of multiple sets? The Cartesian product of multiple sets will have to be denoted by ordered n-tuples. So if A1 has small a1, small a2, and an, then in the same order we have to write a tuple. And in other words, we have to write tuples for all of them. Next topic will be relations. So whenever we are studying about relations, you have to understand that a relation, it is denoted by the capital letter R. It is a subset of the Cartesian product A cross B. Okay, so R is a subset of the Cartesian product A cross B. It is called a relation from the set A to the set B. And the elements of R are ordered pairs A comma B, where the first element belongs to A, that is A belongs to A and B belongs to B. Example, so if you have a set A is equal to ABC and B is equal to 0, 1, 2, 3, then the relation over here has been defined. It will be a subset of A cross B. Okay, and a relation from a set A to itself is called a relation on A. So if we are speaking about a relation R, and which is a subset of A cross A. Okay, now the next thing is using set notations with quantifiers. So for this, whenever we are using quantifiers, you remember the quantifiers universal and existential. So if x belongs to the set S and P of x denotes the predicates, then this denotes the universal quantification of P of x over all elements in the set S. Okay, this we have studied in the earlier class, that is quantifiers with restricted domain. So the domain was restricted to maybe natural numbers or x being greater than 0. The only difference is over here x is being in subset S. Okay, so in other words, if you remember, we used to represent our universal quantification with the implication. So over here for all x, if x belongs to the set S, implies P of x. Okay. And similarly, in the case of existential quantification, we were using the connective and, so the same has been expressed over here. Let's see an example for understanding these statements. What do the statements for all x belongs to R, x square greater than 0 mean? So for this, for all x belongs to R, x square is greater than or equal to 0. What is R? If you remember, R is the set of all real numbers. All real numbers. This statement can be expressed as the square of every real number is positive. Okay. This is the statement, and this statement is true, right? Because for every real number, whenever we square it, it becomes positive. Now, what about the second statement? For some x belongs to Z, okay, so over here, Z is the set of integers, and this statement is saying that x square is equal to 1. Okay. Now, is there an integer where x square is equal to 1? Yes, we have two integers. X is equal to -1 and x is equal to 1. In both the cases, x square is equal to 1. Okay. So, there are two integers for which this predicate is true. So, in this case, since we are speaking about only existential quantifier, this statement is also true. Let's see the solution. So this statement, x square greater than or equal to 0, it is the square of every real number is non-negative, or instead of non-negative, you can even write positive. Similarly, for this one, the statement is there is an integer whose square is 1. Examples are x is equal to 1 and also x is equal to -1 or x is equal to -1. The next is truth sets and quantifiers. So given a predicate P and a domain D, we want to find the value, truth value for P to be the set of elements X and D for which P of X is true. So this is denoted by if X belongs to D such that P of X. Let's see an example. What are the truth sets of the predicates P of X, Q of X and R of X, where each of them are defined in this way? P of X, let's see each of them one by one. P of X is mod of X is equal to 1. And what is the domain? The domain is same for all the cases. It is the set of integers. It is the set of integers. Now in this case, we are saying what is the truth set? So for which values of this domain is this predicate true? That is what we are supposed to find out. So mod X is equal to 1. What are the integers for which X value will be true? So suppose if we take X is equal to -1 or X is equal to 1. What is the modulo of -1? 1. Similarly for 1, 1. So X is equal to -1, the set of -1, 1. Or you can say, let's make it the set A. Okay, if A is the set of -1 and 1, then your predicate P of X is true. Now the next one, over here, this is not x2, it is x square. Okay. We want to find the set of integers for which x square is equal to 2. What are the set of integers for which x square is equal to 2? Is there any integer for which if we square it, it will become 2? No, there is no such integer. So in this case, let's denote it by B. B is a empty set. Why is it an empty set? Because there are no integers for which x square will be 2. What about the third one? The third one is mod x is equal to x. Now in this case, mod x will be equal to x if and only if our x is greater than or equal to 0. Okay, so this is a set of non-negative integers. Okay, So let's see the solutions. If you remember here, mod x is equal to 1. This is being satisfied by minus 1 and 1. For x square is equal to 2, it is an empty set. And what about the truth set of R, for which mod x is equal to x? If and only if x is greater than 0, okay. Suppose if we take x is equal to minus 5, then mod of minus 5, which is 5, is not equal to minus 5. So this is not true. Hence, the set of all positive integers, every time we are speaking about non-negative, it means positive integers. So z plus satisfies this predicate. Okay, so this is the end of sets. We will continue the next topic in the next class. Thank you.